I've got a poll for you. Would you go ahead and answer the poll question? I'm trying to remember all of these things, get the poll question, get the exit tick ready, make sure you got your presentation ready, make sure anyways. Make sure you log into all 3 computers. So what we're going to do is we're going to try to take a function that looks like this, and we're going to try to represent it with this is called a power series, the geometric series in this particular example. But here's the big idea I want to make sure I get right now, okay? Remember, the pink curve is the actual f of x, right? All the other curves are approximations for that pink curve, correct? Where are those approximations best? At 0. In fact, not just 0, but anything that's really, quote unquote, close to 0. Would you guys agree? Now, the reason I'm mentioning that is you might think, good Lord, Mr. Allen, that warm-up was rough. Guess why this is so very important? That tells you where you can use that power series and where you can't use that power series. If you get outside of this interval of convergence, guess what happens to your power series or your series? It's going to diverge, which tells you absolutely nothing. So we got to make sure that we know this. So what I'm telling you is all these curves, and by the way, this is just the partial sums there, S11. We did a Taylor polynomial, if you want to think about it that way. We did the 11th Taylor polynomial. As long as we're kind of, quote unquote, close to the center, then those approximations are really good. They get really bad when you get out here. Like, look out here. These are really bad. They're not good, right? And I wouldn't even want to guess out here, particularly this S2, right? S2 is way over here, and F is growing very rapidly. Does that make sense? So that interval and those radiuses of convergence are very important. So we're going to have to keep those things in mind. The good news is today's lesson at finding those things is actually very easy. Easier than what we did on the one. Okay, so I think I mentioned that I'm not doing any baby problems today. So if you have watched my video on Canvas that I posted, good for you. If what I'm getting ready to do right now seems like a little bit much, I would highly encourage you to watch the video that I've already posted on Canvas in the YouTube page there, okay? Or the YouTube page on YouTube. All right, so here we go. This is kind of harder than just a basic one. If you look at this section in the book or online, they would do a much easier one than I'm doing a harder example. The first indication that this one's harder is look what I did. The center is not 0. If I wanted to start with a nice easy problem, I would just start with the center of 0. That would make things a lot easier. But here we go. And let me just say this. Our goal, that very first thing, is we want to make this 3 over 2x minus 1. We want to make it look, I'll put I want to make it look like this. That's my goal. So let me just start with that so that you're not sitting there going, what is he doing? Why is he doing all this? Would you agree that doesn't look like that right now? Remember, R is going to be the variable part, right? This is the variable. And this has to be 1. That has to be 1 there. And the good news is I kind of got a 1 there, but it's actually not a 1. It's a minus 1. Oh, we have one extra constraint here, too. The center is 2, not 0. So that's going to make this a little bit more work. And I'm going to, I hope I gave myself a couple of slides to do this. Okay, good. So here we go. Now, guys, I'm just going to show you how I do this. If you don't like it, you can do a different method that will probably be just as fine. But I'm going to do the following. Okay, so the first thing that I'm going to do is this. I'm going to go ahead and take care of this C value 2. So since the center's 2, just like in the warm-up, if we go back to the warm-up, remember the center was 2? So we had that x minus 2 thing, right? So I know that in this particular problem, I'm going to need an x minus 2. So the only thing I've changed right here is I took that 2x and I changed it to 2 quantity x minus 2. Am I allowed to do that right now the way that it's written? The answer is no. I just broke math. I'm telling you that this thing in purple is not equivalent to that thing in red. Why? What did I essentially do to the denominator? Well, here, let's just work. If you're not sure what I did wrong, let me just show you. What's 2 times x? Well, that's 2x. What's 2 times negative 2? Well, that's minus 4, and then minus 1, so that's 2x minus 5. Is that the same thing as 2x minus 1? What did I do to the denominator? I essentially minus 4. Are you with me? If I minus 4, what do I need to counterbalance that? I need to add 4. So right here, I'll do it in green. I'm going to put a little plus 4. You might want to add this to your notes. And guys, once you get good at this, you don't have to write all these things down. I'm just trying to explain my thinking as I go through this. In other words, what I'm saying is this is now 3 over 2 times the quantity x minus 2 plus 3. Yep. So far, so good, guys? Oh, actually, you know, I'm going to, instead of just asking that, that's just not very productive. Would you please make sure you unmute yourself or raise your hand if I do something or if I screw something up like I did earlier? Let me know. Okay, so now the next thing I'm going to do, and I'm going to erase what I have here to give myself a little bit more room. I'm just going to do this. I'm going to do 3 over 3 plus negative 2. What is that? Should be minus negative 2. Math again, start off. I'm actually not doing anything but rearranging some stuff right now. Okay, let me make sure I got that right. The only thing I did is the numerator didn't change. The denominator, I just took the 2 terms and I switched them around. So I put the 3 first. And instead of this just being plus 2 times the quantity x minus 2, I did minus a negative, which is the same thing as plus. Because remember, I'm trying to make it look like this, right? I'm almost there. The last piece that I need to do manipulation-wise to get this to look like this is I need to change this 3 somehow to a 1. Okay? So how do we do that? Well, we're going to divide through by 3. Okay, so this is going to give us, in fact, I'll show all the work on this step just to make sure everyone understands what happened. I divided everything through by 3. Which gives us the following. 1 over 1 minus negative 2 over 3, quantity x minus 2. And now I'm going to go ahead and rewrite this and just show you something. If you're like sitting there looking at this right now, and you're like, Mr. Allen, I kind of follow you, but I don't know if I could do that. I know I'm doing a hard one. I'm doing a hard one so that you can't say, Mr. Allen, you did an easy one in class. If you're not sure if these 2 things are equal, guess what you could do? Cross multiply and check. I claim that these 2 things are equal. Okay? Okay, so we've got all this stuff done. Now I'm going to erase this stuff in red because now I want to get to In fact, let's get rid of the red completely. Let's do green. I want to compare this to A over 1 minus R. I'm going to compare it to that. So what is A? Well, A is 4. That's easy. What is R? R is a little bit harder. It is negative 2 over 3, and then the quantity x minus 2. That's what R is. Notice that that 1 there is the way that I want it to be. And now I'm going to stop here because now I'm getting ready to build the power series. I just spent several minutes here converting this to something like this. And it took lots of steps. I did as about as hard of an example as I could think of. It even has negative R value in the center of not 0. So this is a tough one. Most of them are much easier than this one. But would you guys agree that I now have this function? By the way, this is f of x. I have a function that has been rewritten to look something like A over 1 minus R. So now we can put this together. In fact, let me see if I can write this again. F of x. I think it was 3 over 3 minus, was it 2x? And I think we got that to be 1 over 1 minus.
It was 2x minus 1 on the denominator.
Oh, sorry, that you were right. 2x minus 1. 2x minus 1. We got that to look like 1 over 1 minus, and I think it was 2/3, and then x minus 2. Is that right? That look good?
Yes.
Okay, just want to make sure we're on the same page here. I don't want to make any mistakes. Okay, we're good. Right there. Yep. Okay, cool. Now, I can now use this. Here's the big step. We are going to use the fact that we are going to go from 0 to infinity of A, R to the n, right? That's an n. Agreed? This is our geometric series. I'm going to call it a power series today. I'll explain why more later. And then we can just go ahead and build this. So this is going to tell us we're going to sum from n equals 0 to infinity of, well, A here is 1, so that's not very interesting. And then R is going to be negative 2 to the 3 to the n times x minus 2 to the n. Now notice R is to the n. This whole thing is R. So I have to take that negative 2 over 3 to the n and the x minus 2 to the n. Okay. I'm going to clean it up just a little bit. Or I'm going to write it the way I think I would like to have it written. First of all, that 1 didn't do anything, so I can get rid of that, right? I'm going to go ahead and change that negative 2/3 to the n to negative 1 to the n, and then multiply that by 2 over 3 to the n times x minus 2 to the n. I think that's how I want to write my final answer here. I like that alternator to just be a negative 1. That's just my preference. It just sticks out to people. It just kind of like screams in their face. Hey guys, this is an alternating series. Now I'm going to make a couple of notes here. Actually, I'm going to make one note. Let's just call it note. Remember, our center was 2, right? Yes, our center was 2. So here's my question. How am I going to find the radius of convergence or the interval of convergence based on this information. Well, we can do the ratio test, right? But I'm going to go back a couple of slides to this slide right here. And I want you to look carefully here. This says, take the x, which by the way, in our example, what was x? Essentially the r, if you will, right? Take the r, the absolute value of r, and it has to be less than 1. In other words, in this particular problem, we just need this 2 over 3 absolute value of x minus 2 to be less than 1, correct? So how do I get that 2 over 3 to the other side? Well, you multiply by the reciprocal. And that'd be what, 3 over 2, that's 1 1/2. That tells us the radius of convergence is, I'll write it as 1 1/2. 3 over 2, the same thing, right? Where's our center? We've already said that. The center is 2. So that tells us that our interval of convergence is going to be, well, I think it'd be what, 1/2, because you would take 2, subtract 3/2, I think that's 1/2. And then you take 2 plus 3/2, which would be 3.5. So I don't like 3.5. I'm going to write it as 7 over 2. And that's your interval of convergence. Now I will note, you do not need to check the endpoints here. And the reason that you do not need to check the endpoints here is because we built this on a geometric series. Since we built it on the geometric series, we know that those endpoints are going to diverge. Just like I said a few minutes ago, in fact, let me circle this here, and put a box on that, because that's part of the answer. So I'll put answer. Yes. Yes. Yeah.
Is the left endpoint, isn't that negative 1/2? Or am I just dumb?
You are not just dumb. You would not be in this class if you were dumb. But I think 2 minus 1.5 is, I think, 1/2. Does that make sense?
Is it 2 minus 1.5, or is it 1.5 minus 2?
It's, the center is 2. So now I'm going to subtract 1.5 more. So I think that would just be 1/2.
Okay, I see.
Yep, good. Guys, let me just say this again. This is not a baby example. I did a harder example. If you want to see an easier example, I encourage you to watch my video, which hopefully you've already done. This is a harder example. The reason it's harder is for a couple of reasons. Number one, C is equal to 2. Anytime the center is not 0, I shouldn't say anytime, almost every time though, it's going to be harder. Because then I had to deal with this whole factoring piece. The other thing that makes this thing a little bit harder is I put this 2 right there. That also made it harder. And since that was 3, there's actually, maybe there's some sort of conclusion you can jump to there. But I encourage you to work these out. Try not to jump too many steps. So let me go over that process one more time just to make sure that we're clear. This slide was the most important slide of what I did. This slide, I took the function right here, and I wanted to write it. I want to write it in this form as much as I can. I want a 1 right there. I don't care what that is, but that's some number. In this case, I think it was 1, just coincidentally. And then I want all the variable stuff right there. And so that's what I got to here. So that told me, first of all, that's always 1. This is always 1 if you do it correctly, because that's what the formula told us way back here. It has to be 1 right there. Now, this does not have to be 1. It just was in this case because there's a 1 in front of that. This is all the variable stuff. This turned out to be a equals 1 just coincidentally. It could have been 5. It could have been a third. It could have been radical 2. I don't know. And then this is all your variable stuff. So then once you have it written in this form, going to use this idea here, and it's that summation n going from 0 to infinity of AR to the n, that geometric series that we did section 8.2. So that brings us to the second slide. Only thing I did up here is I just rewrote it. And then I knew, okay, there's R, here's A, put A, which is 1 in for that, R, which is all of this stuff, in here to the nth power. So that made that negative 2/3 to the n, and that x minus 2 to the n. And then I just cleaned it up. This is correct right here. But this is the way I like to write it. If you don't like writing like that, you can write it slightly differently. I really like to have that guy kind of separate, though, just to make sure everyone's very clear. That's an alternating. In fact, this is really what we call a power series. And again, I'm going to come back to that later in the lesson. Does anyone have any questions on what I did there? Hard example. If you followed it, you should feel pretty good about yourself, because if you understand this one, the others are much more straightforward. Okay? All right, so let's go ahead and move on. Express 1 over 1 plus x squared as the sum of a power series and find its interval of convergence. Now, I'm going to tell you right now, this looks harder, doesn't it? Doesn't this look way harder? It looks harder because you're thinking, wait a minute, Mr. Allen, you said I want 1 over 1 minus r. This is squared. Oh my gosh. Oh, and there's no minus. It's okay. Let's play the game. So we've got 1 over 1 plus x squared. I want to make it look like this. Well, that 1 is already right there. So how do I make plus x squared look like that? Well, I'm just going to do 1 minus x squared. That's not hard. And in this again, guess what a is? It's 1. We pretty much already got the answer here, don't we? Now let's be careful. Let's make sure we work this out the way that we need to. So that tells us, in fact, let me write this in purple. A in this case is again 1, and r is going to be negative x squared. And now we can go ahead and build our power series. The sum, n going from 0 to infinity of a r to the n. That's what we did in the past. So this is just going to be the sum. Actually, let's go back to red. And the sum, n going from 0 to infinity. A is 1, so that doesn't really help me anything here. I just need to do negative x squared to the n. By the way, that's the power series. Now I'm going to clean it up a little bit, but that was actually super easy, wasn't it? You might be thinking, Mr. Ryan, you should have done that one first. I know, I did a harder one first. Now, I'm going to do a couple of things here. I'm going to say that this is the sum from 0 to infinity. Now, what happens when you take a power to a power? Well, you could make this 2 times n, which is just 2n, but I'm not going to do that. I'm going to do the following first. Just stay with me here. I hope this kind of makes sense. Would you guys agree with that, what I just did there? All I did is I know I'm doing there's a negative 1 in front of this x, and it's to the n. So the very first thing I do whenever I see something, I pull that out immediately. If you don't do that, you will probably, well, I shouldn't say one, you may make a mistake, and I don't want you to make that mistake. And I'm going to do one more step. Can you guess what my next step is going to be? Now is when I'm going to take that 2 times n. So it's going to be negative 1 to the n, and then I'm just going to write this as x to the 2n. There's my power series. Written the way that I would write it. Now I have a question. What is the radius of convergence on this one? Yeah, yeah,
Is it just 1 to 1?
it is.
Or
So
negative
the
1?
radius of convergence is 1. So the interval of convergence is -1 to 1, excluding the -1 and 1, because again, we're using a geometric series. Now, if you were really freaking out because of that first example, hopefully the second example has made you feel a little bit better. Now, before I go on to my next topic here, I want to talk, I guess I didn't need an extra slide here, but anyways, I thought maybe that might take more room than I needed. Let me explain what we just did in this problem. We just took a function and we have converted it to a power series, a geometric series. I'm going to call it power series because that's kind of what we're doing in this section. And it turns out that as long as we use this power series for these values of x, everything is perfectly well defined and wonderful. If I pick a value of x outside of that interval, -1 to 1, then it's going to diverge and it's not going to work. The other comment that I want to make right now is this. What is the difference between this and what we did in section 87? When we talked about like Taylor polynomials and Maclaurin polynomials. What is the difference between what I just wrote right here and what we did back then? Yes, these are infinite. Correct. These are series. This is not a finite number of terms. This is an infinite number of terms which will, in this interval, perfectly replicate that function. Okay, does that kind of make sense? All right. Comments or questions on this example? This one was a little bit easier than the last one. The big idea, though, is this. This is the big idea. Yes, yeah.
So way back when you found r is -x²,
Yes.
can you just use, if it doesn't ask you to express it as a power series, can you just use the idea of a geometric series to find the interval of convergence?
Yes. That's what we're doing. Now, I'm going to we're going to come back to why we're calling these power series. I'll come back to that, and I hope I do a good job of explaining to you why this is helpful. Because honestly, right now, some of you might be saying, you know what, Mr. Allen, if this was the function f, I feel very good about just that. Why would I ever want to do this? That seems way harder, right? Doesn't that seem way harder? Like way harder for someone to understand than this? We'll get to that. All right, so there's a blank slide there, starting that last one. This is a blank slide. I didn't really need that. Okay. I'm kind of getting to that point that I wanted to make right now. So you might be saying, Mr. Allen, who cares? Why would I want to ever do this? 1 over 1 plus x squared seems fine to me. Why would I ever do this? Well, the sum of a power series is a function, f of x equals sum from n equals 0 to infinity of c sub n, x minus a to the n. Now, guys, right here, this is that a, r to the n, right? This is the same thing as that. Whose domain, so remember, when we talk about a function, the values of x for which it's defined for, its domain will be the interval of convergence. So that's what I've been telling you. That interval of convergence is very important because if you get outside that interval of convergence, that power series is no longer going to represent it well. We would like to be able to differentiate and integrate such functions. In fact, I'm telling you right now, on the AP exam, on the free response, they're going to do this to you. They're going to give you a function. They're going to say, hey, what's the power series for this function? And then they're going to ask you to do calculus to the function. Oh, by the way, let's just go back to this. Please tell me verbally right now, what is the antiderivative for this? It is arctan. Old brick to you, Midori. That's exactly what it is. She knows what she's talking about. Arctan. By the way, I'd like you to think about how does your calculator know how to deal with arctan? I'll tell you how your calculator deals with arctan. Deals with it right here. It represents it as a power series. What I'm telling you is, in fact, let's go back to it. Guess what the only term in this infinite number of terms that involves the variable x? Just that one right there. It's a monomial, which was one of the questions on the exit slip last week, right? How hard is it to integrate or differentiate monomials using the power rule? It's very easy. So you can actually perform calculus on these much easier. In fact, you might have, how in the world did anyone ever figure out that the antiderivative for this was arctan? Well, power series. Okay, so here we go. Theorem 2. Did I skip anything? Yeah, term by term differentiation. If a power series, that's what this thing is, has a radius of convergence that's greater than 0. In other words, it has to be defined, its domain has to be defined on something besides its center. Remember, they're always going to be defined on their center. But we don't want the radius to be 0 because then it's basically useless at this point. Then that power series can be represented like this. Here it is in compact form. Here it is in expanded form. Now look carefully, and we're going to come back to this next week. What is the derivative of constant C0? 0. So this term is gone. What is the derivative of this? Well, this is a linear term, so when I take the derivative of it, it's just going to be C1. Look at this term here. I'd have to use the chain rule, but this would become 2 times C2 x minus a. And we would continue on down the line. Now look here. Here's the important idea. Big time important idea. If you miss anything, don't miss this. This is the only thing that has x as a variable. What is the derivative of x minus some constant a to the n? Well, it's n times the quantity, leave the quantity alone, to the n minus 1. That's just a power rule for differentiation. Similarly, but now let's go the other direction. Let's talk about integration. How do I integrate something like this? Well, guess what you do to the n? And plus 1 to it, don't you? And instead of multiplying by n in the front, you divide by n plus 1. Notice, now here's where we do need to be careful. Put a little asterisk next to the integration. Don't forget that whenever we integrate, we have to do that constant, plus c. That plus c is arbitrary, and it would depend on the initial condition of the problem. Now, guys, when we started this chapter, I told you that I felt like I didn't do a very good job of emphasizing this the last couple of years on the calculus. Guys, there's a lot to this class, isn't there? There's a lot of minutiae to this class. And I'm trying to do a better job of telling you how the reason we like power series is because it's easy to differentiate and integrate them. And by the way, we can do double integrals or multiple derivatives if we want. So I think that brings us to our last example here. Okay, good. Guys, I'm going to give you my last poll question for the day. And as I get ready to do this last problem here, I'm also going to make sure I've got my exit ticket because last week I forgot to send you guys an exit ticket. Try not to do that again today. There's a poll in the poll, so if you would answer that, that would be fantastic. Last question here. How are we doing? Okay, we're right at, well, just under an hour now. This is going to go fast. This is going to be the fastest example, I think. This is a well-known function, and you guys don't think it's well-known, but it is well-known to the mathematics community. It's called the Bessel function. And they use this J naught of x as the notation that they use. I don't really care that you know that. If for all you care, they could just call it f of x. And here it is. It looks kind of scary, doesn't it? But my question is, and it's not a hard question, is what is the derivative of this? So if this is f of x, I'm asking you, what is f prime? And by the way, I would encourage you, if you're really interested in the Basel function, if you want to see the explicit formula for the Basel function, just Google it and just look how fun it is when it's not written this way. It is way worse than this. Now here's the beautiful thing. What is the only thing in this, I'll call this a sub n, what's the only thing in a sub n that has a variable x? What's the only thing that has a variable x? Just that piece right there. So let's go ahead and find its derivative. Its derivative is going to be n from 0 to infinity. Negative 1 to the n is not going to change. 2 to the 2n is not going to change. N factorial squared is not going to change. But guess what's going to happen to that x to the 2n? It's going to become x to the 2n minus 1. Oh, and by the way, what also needs to be multiplied in the front of this thing since I did the derivative? 2n. And I'll put that, let me put that in red. Let me put both of these things in red and make them stand out here. Let's get rid of that. Let's do it in red. This is going to be 2n minus 1. And then you got to multiply it by 2n. That's what the power rule for differentiation is. In other words, I think the way I would probably finish this guy off, maybe, is I would say it's n starting from 0 to infinity. And then I would probably just go ahead and put this negative 1 to the n on the top. Now, you see that 2n in the front? That's in the numerator, correct? Does that affect anything here? Well, the answer is yes. Okay, so you have, let me kind of write this up here. You have 2n up here, and then you have 2 to the 2n down there, right? Oops, there's a 2 there. 2. Right? So do you have a power of 2 in the numerator? You do. So how do I, if I bring that down, what does the 2 to the n exponent change to? Like, let me give you an easier example. If this was x over x to the 2n, what would that be equal to? 1 over correct, x to the 2n minus 1. So this is going to become 2 to the 2n minus 1. That n is still there, unfortunately, so I can't really do much with that. I'm going to go ahead and leave this n factorial squared alone. But I'm going to go ahead and just leave this in there, and then I'm just going to change this to 2n minus 1. I might put that in parentheses, and I think I would call that a day. There's the derivative. Oh, I guess I should tell you the radius of convergence. And this is one of the really fun things about this particular function. The radius of convergence is infinity. In other words, it works for any value of x, which is very nice. Now, guys, I know that looks really crazy, hard, difficult. If you got this part right here, if that made sense to you, check. You got the big idea. That's what I want you. And by the way, again, I told you, I'm not doing any baby examples today. This is a really complicated power series, right? That is not a friendly looking power series. It actually has a lot of application problems. In fact, I think I made a note of that. Now, I would like you guys to try the integral. Would you please try to do the integral? I did the derivative, try the integral, and then that's where we're going to leave things at today. And I'm gonna send you the exit slip right now too, so I don't forget. We're right at the 1 hour mark.
I guess we're a little bit past the winter. I'm thinking of fifth period.
All right, let's go ahead and finish this out. What's the very first thing you need to write? Hopefully you wrote C. Did you put the plus C? Remember, whenever you integrate, you need to put that plus C. And then you're just going to get the summation from n equals 0 to infinity. And then I'm going to write it just probably how I think that you guys wrote it. But maybe you wrote it a little bit differently. Times, and then this should be x squared, or x to the 2n plus 1, thank you, divided by 2n plus 1. That's your answer. By the way, the radius of convergence here is also infinity. But we're not going to worry about that. Okay, guys, that's it. That's it for today. So I hope I've made an impression on you about why this might be useful. We looked at how we can make a function. And by the way, the function kind of has to be written, you know, like something over, you know, something, you know, plus or minus, you know, x or whatever, something like that, right? How to convert that into a power series, that's what we're trying to do here. Okay, and then I'll call that R. We did this. And why we're doing that is then we are allowed to do these derivatives and integrals of some very complex functions and make them work out very nicely. And so I'm just telling you right now, if you think back to that second example I did where I asked Midori what the integral was, he figured out what that was. We could do the integral of that even, and we can actually, you know, do some really interesting things. The point of the power series is that we can do the derivatives and the integrals relatively easily on these power series. I'm going to shut up now. Thank you guys for paying attention. That is it for today. Tomorrow we will meet. We will practice converting functions to power series. And I think, let me make sure I'm not telling you wrong. I think the only thing that you guys need to be worried about in the coming days is, oh, not that class, that's geometry. I think you guys have something coming up right before spring break. I don't think we have anything next week. I think it's the week after that. Sorry guys, I teach geometry, calculus, and calculus BC. So this is this week. So yeah, so this week I gave you a sample quiz, which is going to be sections 8, 7 through 8, 9. And so we'll have a quiz next week, it looks like. So just to kind of keep that in mind. Okay? That's all I got. If you have questions, I'll stick around.
Have a great day, Mr. Allen.
Yeah, have a great day.
Thank you, guys. Have a good day.
Sorry I wasn't in class today.
Say it again.
I'm sorry I didn't make it to class today.
Have a great day.
I don't want you to apologize. See, Stephen, Jack, you don't need to apologize. I actually told everyone that was here in class, and they were actually really excited that you weren't here in class today.
Oh, yeah. Awesome.
There
I
was
just
only
like-
there was only one person that was really upset,
Who was really upset that I wasn't in class?
Mr. Allen was.
See, and that's the most important person in class.
I'm just kidding. I think they missed you too, but nobody said anything, so maybe they did miss you.
Yeah, maybe. Well, anyways, have a great day.
Will you be back next week?
Yeah.
Okay, cool. See you soon.
See ya.
Have a good day.
Thank you, James. James, I think I owe you a Smarty, man. Almost blew up that first example. Or was it the warm-up? It was the warm-up, wasn't it? Regardless, you saved my tail. I appreciate that. Here you go. Can you catch? Smarty for you. Andrew, are you there? You guys know, you see this face on it. Is that him? That's not him.
No.
Who is it?
I don't know. He's had it since like middle school.
I know, it's kind of interesting. So, there's a lot of people that have like interesting things, and I'm like, I don't know, there's probably a funny story too, and I'd love to know the story.
Rich has the same guy.
Rich does too?
Yeah, it's a different picture, but it's the same guy.
Is it someone from TV or something,
I
or
think it's from like YouTube.
YouTube? I would love to know who that is.